Okay. Please apology to everyone as I'm having common cold. You can maybe sense it from my voice. I think you can bear me with that. I'm going to talk on biophysics, the physics of life. Okay. The outlines of the presentations is going to start with introduction, matter and the energy, historical development of biophysics, essentials of biophysics. Application biophysics as a result of coining two broad terms of physics and biology. Next slide, please. Okay. Yes, the word biophysics comes as a result of coining two words of biology and physics. As we all know, biology simply means the study of life, while physics is a branch of science that concerns mainly with the study of properties and introduction and interaction of matter and energy in time and space. From there, we can now simply say that biophysics is an interdisciplinary that concerns with the application of the principles and the method in physics as well as in chemistry, together with some mathematical analysis and computer models. In order to understand life from through its dynamics interaction and ultimately to the supramolecular structure of life. A biophysicist or biophysics try to strike balance between the complexity of biology or complexity of life with the simplicity in the law and the principle of physics, so that it can easily give understanding pattern of the formation in life processes from which we can easily form principles and models. Next. Okay. Saying, or as we all know, physics concern merely with the interaction of matter and energy in space and times. Atoms and molecules in motion create heat, pressure, and diffusions, not only in physical objects, but also in biological matter. Heat, as we know, ensures homeostasis in living organisms or in human body, so to say. Pressure as well helps in regulating a lot of activities in the body, while the diffusion ensures exchange of substances, especially across molecular membranes. Measurement of these parameters gives valuable information on molecular number in the body's size, mass, and shape. Human body, or to say living matter, moves in response to an external gravitational or electromagnetic fields. Rate of their movements in response to such gives information on mass, charge, size, and shape of living matter. Biophysicists, the understanding of biophysics is that both living and non-living matter is composed of matter and energy. However, the most important difference between the two is just the way matter and energy is arranged in extraordinary way in living matter that makes it to have a special characteristics of exceptional complex arrangements of living cells from submolecular level up to supramolecular structures. These arrangements form dynamic forever and changes in
you understand? Did I?
And in complex interactions, meaning it takes place dynamically, and there are changes, let's say from molecular level to cellular level to tissue level organs and organ systems level. Next slide. Okay, understanding life up to molecular level, which is part of the interest of biophysicists, help us in giving a good understanding how the set dynamic changes occur and how also conformational changes comes into reality as a result of interactions and the regulations of matter and energy through a controlled manner. Study of these processes tied in the fundamental structure and the functions of life building blocks and allows us to study diseases. Any perturbation or to say any distortion in the extraordinary way of arrangement of matter and energy in the human body that resulted in perturbation of the calibrated equilibrium resulted to what we call disease. If this distortion continue for a long time and in an amplified manner, it may result in the death of the cell, which is fundamental of life, and this may result in the loss of life. At this juncture, it is important for us to know that in biophysicists, in their trials, in their pursuit of understanding things from its molecular level, they also imbibe ideas from biochemistry together with the instrumentation of biophysics. This will help them in providing the good understanding and have in investigating biological processes using tools or principles and models of chemistry and physics. Okay, this slide is trying to give us having understanding that biophysics is trying to also imbibe some ideas from biochemistry and trying to understand life from its molecular levels. Here is the chemical composition of the human body. We can see that most of body, about 70% is made of water, 16% is, of course, protein, well, minerals, and parts. Parts also have 16%. Carbohydrates that give us energy is also managing with only 1%. Then minerals having 6%. We can see that the important elements in the body, of course, there are about 25 elements, but the important ones are just 5. That is carbon, hydrogen, oxygen, magnesium, potassium, and sodium. Next slide. Saying that 62% of the human body, or even more than that, as the case may be, is made up of water. This does not ensure that these chemicals or this water content of the body is evenly distributed. Certain organs or certain substances appreciate more water levels than others. As you can see here, liver contains 86% of water, while blood and kidney having 83% respectively. Bone is the organ that is having least a content of water, about 22%. Next. Okay, Now, for us to appreciate biophysics more, it is important to go back to its historical development. Of course, as we all know, science only became details about 1800 when it was changed from natural philosophy to what you call science, and then broadly divided into physical science and biological science. Until then, biophysics, of course, was not in being. Therefore, it is relatively a new branch of science compared to other ones of, let's say, normal physics and chemistry. However, its foundation can be traced back to 19th century, and it was firstly instituted in the group of biophysicists in the Berlin physiological group. Notable physiologists that make the foundation for biophysics include Hermos, Raymond, Ernest Brook, and Carl Locke. We can all possibly be able to remember Adolf Fink, especially his important theory of or law of a principle of diffusion that explain how substances can be changed across a molecular or cellular membrane. He established one important book, the name is here in German, although it may be called the medicine or the medical physics, but then it refers to biophysics, because as we are going to see later, medical physics is also a part of a biophysics. This is our cover of the third book of Adolf Speak. Okay. German physicists, or to say German physiologists, continue to champion the foundation for biophysics up to the first half of 20th century. They even championed the study of electromagnetic fields. We can all remember the Roentgen discovery of X-ray in 1895. Of course, in 1944, popularity of biophysics increased and amplified as a result of the book, What is Life?, written by Australian physicist Aaron Schrodinger. He published the book after a series of public lectures on chemical and physical principles of life. This aroused the interest in the book. He proposed the idea that there was a molecule in living things that contain genetic information on covalent bonds. This is what aroused the interest of James Watson and Francis Crick in 1953 to characterize the genetic molecule, that is the DNA, after they confirmed with the ideas of Schrodinger and the Rosalind Franklin's X-ray crystallology. They comes off with double helix structure of the DNA. All these are as a result of the book written by Schrodinger, trying to explain how life can be understood using physical and chemical principles. By mid-20th century, of course, physical programs have sprung up and gained popularity both in other countries, not only Germany. From 1950s to 70, biophysics research occurred at faster rates than ever before. Great progress in biophysics were made during this period, in which biophysical principles was largely employed in treating diseases. It also gave huge contribution in coming up with powerful vaccines against infectious diseases. At that time, and of course, even in the present days. Because remember, now, what are the goals? What is the aim of biophysics or biophysicists? Biophysicists broadly concerned with trying to understand biology in a quantitative way. As we all know, biology is trying to show how complex life is, while biophysicists is trying to give it a quantitative meaning so that everyone can easily understand it in its regular or its irregular form. Biophysics study the effects of radiation and electricity on living things. It is also directed to determine the structure and dynamics of biological molecules and of the larger architecture into which they assemble. Inventing new methods and instruments for view these dynamics or to view this dynamic structure in action in living matter is part of the goal of biophysicists. They are also increasingly concerned with the mechanical properties of biophysics. As we can see, it is also the principles of biophysics are largely employed nowadays in physiotherapy and other physical body issues. Now, what are the essentials of biophysics? Essentials of biophysics include, it describes how atoms are arranged for work in DNA and the protein. Biologists can only say that, for instance, there are 20 essential and non-essential proteins. But how, in what way are they arranged? Or what is the meaning of the arrangements in DNA? And why is it that the essentials can be obtained naturally in the body and non-essential ones can be synthesized from the body we eat? Biophysics also describes how proteins work, being them what builds our body. Biophysics can also be used as understanding protein structure for discovering how biological mechanisms work in health and in diseases. Why is it that the more the arrangement of proteins, especially in the DNA structure, is perturbated, that resulted to death? How does that happen? Variation in proteins makes people to respond to drugs differently. This answer is also part of the work or essentials of biophysics. Biophysics also helps us to understand these differences in an open way for new possibilities in drugs dosage, diagnosis, and disease control. Biophysics principles are the ones that even pharmacists use in assessing the drug dosage. Physicians also use it in diagnosis of their patient and also trying to come up with the controls of diseases. Applications of biophysics. Of course, biophysics being it's very broad. Its application largely depends on societal needs. All we know is that it helps in inventing powerful vaccines against infectious diseases. Infectious diseases may be the disease that is a problem in West Africa may not be in the Western Europe. So therefore, societal needs determine how the can be applied. So I think also describe as the best way of controlling diseases of metabolism, such as diabetes. It provides tools and understanding diseases of growth, that is a malignancy. Of course, medical physicists are very good in understanding the physics of cancer, and that one goes a long way in addressing it and also augmenting its effects. Methods of biophysics are increasingly used in environmental protections, especially in bioremediations. Biophysicists are also inventing new instruments and techniques for detecting, purifying, imaging, and manipulating chemicals and materials for health and life to continue. Biophysics also discover how to modify microorganisms for biofuel and bioelectricity. Part of the problem of the present day world is global warming as a result of climate change. Biophysics is trying now, knowing fully how life is in microorganisms. They are using it in a systematic way to change, to modify microorganisms so that they can produce biofuel. That fuel can be used in bypassing a non-renewable fuel that gives rise to global warming. Part of the application of biophysics also include discovering the biological cycles of heat, life, water, carbon, nitrogen, and oxygen in the ecosystem. It harnesses microorganisms to clean water and to produce drugs also. Now, what is the instrumentation? All these applications are only possible having a good understanding or utilization of instrumentations in biophysics. Measuring systems are used to provide quantitative information about the parameters we mentioned of biological importance. These include bioelectric potentials from models, eye, neurons, heart, brain, as well as blood pressures, and also for muscles. The electrical or the signals that we may measure or obtain from the mentioned biophysical parameters can be in mechanical or electrical form. However, the interest of biophysics is largely of electrical signal. The signals, however, are very, very small. They need to be amplified for a better display and interpretation. From last year, if you can remember, there was a presentation in the similar presentation of signals, electrical signals from models that we call electromyogram, signals from the heart, electrocardiogram. I could remember there was a presentation that was mainly on electrocardiogram last year. Also, the electrical signal from the brain, we can analyze them through what is called electroencephalogram. Signals also from eye can be electroretinogram and the electrooculogram. These ones may possibly be new, maybe compared to other ones. Retinogram actually concerns with the ability or the relationship between the retina, the information it sends to the brain through optic nerves, while oculogram is trying to measure electrical pressure from intraocular pressure. Okay. Cardiovascular instrumentations are part of the most important instrumentations of biophysics. And they include bioelectrical potential, as we mentioned, patient monitors, especially in intensive care units, Also, you are, or they operate based on biophysical principles. Amplifiers that we use in analyzing whatever electrical signal is, pacemakers, and defibrillators. Next slide gives us just the image of implantable cardioverter defibrillator, and as well as a pacemaker. Of course, a defibrillator is a device that helps maybe if there are irregular contraction in the muscles of the heart. This may result to a cardiovascular accident. Defibrillator are implanted internally or externally to help in addressing this irregular contraction of the heart. So, what do you call it? Heart failure. Of course, it incorporates pacemaker. However, pacemaker differs from implantable cardioverter defibrillator. While the defibrillator can supply or can give both low and high pulse of electrical signal, pacemaker only gives low pulse. Pacemaker, we have natural ones in our body that help us, in our heart, that helps us maintain normal heartbeat. There are instances where normal heartbeat may be perturbated. In that case, artificial pacemaker has to be implanted in someone's heart so as to complement the task of natural pacemaker. All these ones use physical signals, electrical signals. Okay. These ones are just images of tools that are used in patient monitors that also use electrical signals. These are largely used in, as I say, in ICU units, that is intensive care units, to maintain normal electrical signals so that normal life can continue. Now, application of electrical and magnetism, electricity and magnetism in medicine. Having said electrical signals, it's a common knowledge of physicists that wherever we say electrical signals, magnetism has to come in. So they are complementing one another. Wherever we have electricity, we must have a magnetic field there. The effect of them in the body, important effect of electricity in the body include thermal effect and the electric shock. Both of them are employed in trying to help someone to keep on with his normal life. Take example of electric shock. The defibrillator we mentioned in the previous slide, it largely employs electric shock, but in a safe way, to bring back normal contraction of ventricular muscles in the heart. Thermal effect of electricity is also employed largely in physiotherapy or in, let's say, addressing some inadequacies, let's say, of a newborn. We have infrared, we can, if a newborn baby is common problem that's called deficiency in bilirubin. Of course, we can use a thermal effect of electricity through supply of infrared radiation to deficiency in bilirubin. medically, the condition is called jaundice. High frequency electricity is also used in medicine as well as low frequency electricity. Current research involving electricity applied in medicine is continuous. Pieces of diagnostic X-ray is part of the important aspect of biophysics. I only mentioned the important aspects. I've been pulling on that these things have already explained in the previous presentations. Sound also in medicine is largely used in understanding how vocal cords vibrate and gives rise to speaking. Sound is also used in medicine, let's say for diagnostic and for therapeutic purposes. For diagnostic purpose, ultrasound scan is common example. As we know, sound above normal range of human hearing is what is called ultrasound, while infrasound is the one below normal hearing.
Dr. Abba, Dr. Abba, sorry, please, you have 1 minute more so that we can have some time for questions. Thank you.
Only 1 minute?
Yes, please.
Okay.
The time
So,
is up.
okay, the biophysics, there are 3 important major branches of biophysics: molecular biophysics, radiation biophysics, and medical physics. Molecular biophysics concerns understanding life from its molecular level. Let me just rush. It concerns all the specialists in this aspect of biophysics may work in genetic engineering and as well as in academics, because they wish to merge the two. Radiation biophysics is also sometimes called health physics, and it's part of science of radiation protection. It's mostly concerned with the safe use of radiation in medical, scientific, or industrial work, trying to help humans against biological effects of ionizing radiation. Specialists in this aspect may work as researchers in environmental protection, in military, in law enforcement agencies. While medical physics, I don't think if I have to even say much in that, having known fully that we are, almost all of us are medical physicists. This is the time constraint. Maybe I have to round it off now. Okay, this chart is trying to give us a bit understanding of how the effect of the radiation that health physicists or radiation biophysicists is trying to address issues in. Ultimately, as we can see, there are radiation of safe limit and non-safe limits that may result to adverse health effects. It may result to carcinogenesis, hereditary effects, or teratogenic effects. Okay, here are questions so thank you for listening. I intend to say these are questions of interest to biophysicists that are, some of them are still unanswered, that are of course of interest to medicine. One, or the first one is, how does life emerges from some collection of those molecules? This is a task, part of the task of biophysicists. Second, how does a single enormously long DNA molecule is untwisted and exactly replicate itself during cell division? Also, this is part of the Nobel questions for biophysicists. These physical properties, also, how does it translate to structure and functions of life of a living cell? And how does behavior emerges just as a result of electrical signal in neurons, that is cells of CNS. How does muscle cells convert to chemical energy in ATP? Thank you very much for listening.